Okay, so good afternoon. Today in this lecture I am going to continue our discussion on the generalization of Euler-Lagrange equations. So, we will primarily continue our discussion that we started in the previous lecture, Euler-Lagrange equations. So, this is a continued portion of the previous lecture. So, in this case in this lecture we are going to do two major cases, namely the generalization which involves Euler-Lagrange equation containing functions of several dependent variables, but only one independent variable, and the other way one dependent variable, but several independent variables. Right. So, let us look at these two cases. We have seen generalization. The first case was functionals containing derivatives of order higher than 1. Right. So, this is my second case. So, in this case we are going to discuss how to generalize Euler-Lagrange for functionals containing several independent variables, right. Euler-Lagrange containing several independent variables, but one dependent several dependent variables, but one independent variables, right. And then the second case will be the other way around. Okay. So, so in this case let me just give a brief example. So, for example, let us look at the motion of a particle in 3D space. The motion of a particle in space, in 3D space, will require us to track three independent three components of position. Let us say they are given by x of t, y of t and z of t, which are the three components, all as a function of time t, right. So, this is one such case where we have three dependent variables x, y, z, and they are all functions of the independent variables, which is the time in our case. And we are going to see that this also follows the standard case of the Beltrami identity, the example that I have just mentioned. Okay. So, let us now start building up the background to figure out the necessary condition in this case. So, first we have to describe the space where this extremal is going to be taken. So, we describe we describe C2 of T0 T1, or the set of all continuously differentiable functions up to second order within the interval T0 T1. We describe this space which denotes the set of all vector functions, q bar from T0 to T1, to Rn. So, the domain of these vectors is picked up from the interval, which is mainly the time t, and the range is all the components of this vector q bar, which is in Rn. So, where each of these components of q bar are C2 differentiable. So, where q k's are in C2 of T0, T1, right. Okay. With the moment we describe the space from where we are getting the vectors, the vector functions, we also have to describe the norm, because that is how we are going to measure the difference when we calculate the variation of the functional. Okay. So, with the following norm, we describe the following norm as the norm of Q. The norm of Q is described to be the maximum among all the components k from 1 to n, the maximum among all the components of the supremum of the absolute value of Q with respect of Qk, where the supremum is taken over all t from T0 to T1, right. So, the norm is the maximum of the supremum of Qk, right. So, now let us consider the functional. So, consider the functional of this form jq bar, which is denoted by the following integral from T0 to T1 L of t comma q bar dot dt, where I define my dot, the superscript dot, as the derivative operator with respect to the independent variable t. Okay. And also that this L that I have described, the integrand of this integral, which is a function of these vector quantities, it is also smooth and has derivatives up to second order, right. So, what I am just saying is L has continuous derivatives of continuous derivatives up to second order, continuous derivatives up to second order with respect to t comma qk comma qk dot, right. And I have that k is from 1 to n, right. Okay. So, let q naught and q1 be in Rn, right. So, now while we are describing our functional, notice that we also have to describe the endpoints, because we have a fixed endpoint case. So, I describe my endpoint with this following vectors q naught and q1 in Rn, and in this case my fixed endpoint problem becomes is written as following. The fixed endpoint problem consists of finding my fixed endpoint problem consists of finding the extremal of j from the set described by S, where S is the set of all q bar which are C2 differentiable up to second order, and has the following boundary condition: q bar of T naught is q bar naught and q bar of T1 is q bar 1, right. Okay. So, then let us also further describe the perturbation, right. So, the perturbation of q bar, let me say that this is q bar hat is q bar plus epsilon times eta bar, right. So, this is now perturbation in each of the components, and I describe, so where I describe my perturbation function eta bar to be the following vector function eta 1, eta 2, eta n, which belongs to the set H, which is also equal to all such etas in C2, T naught T1, all such perturbation functions such that the perturbation vanishes at the end point, right. So, whatever we basically described, for example, the set S, the perturbation set H in the standard derivation of Euler-Lagrange, we have now extended it to describe similar sets for the vector functions, right. Okay. So, then now I am ready. So, the moment I have described my perturbation, I am ready to expand my integrand. Let us go back here. I am ready to expand my integrand L in terms of, let us say, if I have an extremal q bar, I am ready to expand my integrand in terms of the extremal q bar using Taylor series. So, if we were to use Taylor series, let's go to the next slide. So, for small epsilon, the Taylor series implies that I have L of T of q bar comma q bar dot is also equal to L of T comma q bar plus epsilon eta bar comma q bar dot plus epsilon eta bar dot, right. So, where the dot represents the derivative with respect to the independent variable t. So, we can now start expanding using Taylor series. So, this becomes L of T comma q bar dot plus epsilon times, we see that we have the following set of terms. Now, notice that we are dealing with vector quantities. So, we will have n terms, one for each components of the vector. So, we describe it in the form of a summation from k from 1 to n, and each of the components follows the standard expansion of the Taylor series in the standard derivation of Euler-Lagrange. So, eta k del L del q k plus eta k dot del L del q k dot, right. So, and that is it. And then we have the next set of terms are order epsilon square, right. Okay. So, which means that the variations delta j is given by j of q bar hat minus j of q bar, and we just replace the respective integrals and taking the necessary cancellations, we are going to be left with the following integral, which is the leading order term, integral from T0 to T1 summation eta k del L del q k plus eta k dot del L del q k dot, k from 1 to n, right. And let me call this times dt plus order epsilon square terms, right. Okay. So, then the next step of finding the extremal in this particular case is to now reduce, is to try and change this integral in such a way, so that we can pull out these perturbations functions eta k, and to do that we again further use integration by parts, right. So, well, but before that we have to understand that each of these eta k's, they represent the component of the perturbation vector function. So, well, of course, we must say that the necessary condition for q bar to be an extremal is that we must have delta j of eta comma q bar is equal to 0, right. So, what I have is, let me call this, we need to name certain equations. Let me call this particular equation as 1 in the slide 1, and in slide 3 I am going to call this relation, the necessary condition as 1 prime that we need to obey, right. So now what we have is the following. We need to figure out the Euler-Lagrange equation satisfying 1 prime. So to do that, we also want to highlight the fact that the Euler-Lagrange equation for this n component problem is slightly more complicated, but we can resolve the issue as follows, right. So 1 prime is more complicated, more complex, right, than EL equations for one dependent variable case, but we carefully select our perturbation eta prime, which is in our set of perturbations functions H, right. So what we do is the following. We consider the following perturbation. Consider the perturbation, let us say eta 1 in H1, right, where eta 1, where my set H1 is the set of all, so we have a scalar here, the set of all perturbations eta comma 0 comma 0 and so on, such that eta of x0 is equal to eta of x1 is equal to 0, right. So eta satisfies, the only non-zero component also vanishes at the boundary. So here we are considering a perturbation with all components 0 except the first one, right. So certainly this perturbation is also belongs to our perturbation set H, which is this one, right. Now if we are to use this particular perturbation, we see that our Euler-Lagrange equation reduces to the one dependent variable case, and the dependent variable being q1, right. So then, so what have I said so far? So what is being said is, for this particular perturbation in H1, it implies that 1 prime reduces to d dt of del L del q k q dot minus del L del q1 dot minus del L del q1, which is equal to 0, right. So that is my Euler-Lagrange equation with respect to the first variable for the choice of perturbations that we have just chosen, right. So that is my necessary condition, right. Okay. So similarly we can choose perturbation for other components. So similarly, describing perturbation sets for other components, we are going to find that each of the components. So we can repeat this procedure like we did for the first component to the second, third, so on, and we are going to get the following set of Euler-Lagrange equations. The first Euler-Lagrange describes the extremal for the first component. The second Euler-Lagrange equation describes that for the second component. Right, and so on so forth. The nth Euler-Lagrange equation satisfies for the nth component. Right, and we are going to see that this is a system of n. So this is a system of n second order differential equation for n unknowns. Second order differential equations for n unknowns, where the unknowns are q1, q2, qn, which is the necessary condition. for our generalized case with multiple dependent variables. Okay, so we have found Euler-Lagrange, which is a system of Euler-Lagrange equation. Okay, so let me just recap so far what we have said in the form of a theorem or a result. So the theorem says, so we have theorem 5. The theorem says let j from C2 of T0 to T1 to Rn be a functional such that j of q bar is equal to integral T0 to T1 L of t comma q bar dot dt. So this is my functional where my q, which is given by this following vector, where q is this following vector, and L has this function L inside this integral has continuous derivatives up to second order with respect to t qk dot, well, qk and qk dot, right, for each k from 1 to n, right. And then further we describe the set of all extremals to be the set containing vector q, which is C0 C2 of T0 T1 such that q bar of T0 is q0 bar and q bar of T1 is q1 bar, right, and these all belong to Rn. And further we describe, we continue by describing the set of perturbations as H, but then the result is then q bar is an extremal, of j in S if my following set of equations are satisfied. Following set of equations are satisfied where k is from 1 to n, right. Okay. So then let us look at some examples. So the first example, well, here is an extremal, so we need to extremize j of q bar, which is integral from 0 to 1 q1 dot square plus q2 dot square minus 1 plus q1 square plus q1 q2 times dt, right. So we see that in this case the functional has an integrand which has two dependent variables q1 and q2, and both depend on the independent variable t. So if we are to find, well, let me also provide the boundary condition. So where q bar of 0 is q0 and q bar of 1 is q1. Okay. So then to find the extremals we have to write down two Euler-Lagrange equation. The first one being, so before we do that, let me just write down the various derivatives that are involved in the Euler-Lagrange equations. The first one being del L del q1 dot, that is differential with respect to q1 dot, we get 2 q1, right, 2 q1 dot, and similarly del L del q2 dot is also equal to, we differentiate with respect to q2 dot, we get 2 q2 dot, right. So well, we do not have a square here, we have a square here, that is the problem. So we get 2 times q2 dot minus 1, right. And then the other derivative we have to worry about is del L del q1, which is del L del q1, which is equal to 2q1, and del L del q2 which is equal to q1, right. So, that is all what we have. Well, del L del q1, we have q1 appearing here and q1 appearing here. So, 2q1 plus q2, right. So, these are the different derivatives which are appearing in our Euler-Lagrange, and we are ready to write the system of Euler-Lagrange. My Euler-Lagrange for both the variables, the first one, after plugging in the values, we get the first one is q1 double dot minus q1 minus half q2 is equal to 0, and q2 double dot minus half q1 is equal to 0, right. So, then the next set of steps involve solving for q1 and q2, and the standard way to do that is to eliminate one of the variables. So, let us eliminate q1 by differentiating the second equation twice with respect to t and substituting q1 double dot from the second equation, and what we get is an equation purely for q2. So, we get the fourth derivative minus 2 q2 dot double dot minus half q2, which is equal to 0. Okay. So, then the next step involved is we can look at an equation, we can look at a solution for q2 of the form, let us say q2 is of this form e to the power mu t. We can plug this form here, and we are going to get a characteristic equation for mu which is polynomial. So, 2 mu 4 minus 2 mu square minus half is equal to 0, right. So, I have mu 1 comma 2. So, I have, of course, this is a fourth order polynomial equation. We will expect 4 solutions. The first 2 solutions are as follows. This is also equal to plus minus square root of 1 by 2 plus 1 by square root 2, and we see that both these solutions are real, and the second set of solutions are given by plus minus square root 1 by 2 minus 1 by square root 2, which is also equal to plus minus I m, right. So, what I want to show here is that the second set of 2 equations are purely imaginary. So, it is I times some quantity which is a real number, right, where my m is a real number. Okay. So, when we plug all these values of q mu, we are going to get that q2 of t is equal to c1 e to the power mu 1 of t plus c2 e to the power, we get the following linear combination. Okay. And we see that after plugging in, after simplifying, we expect that since the third and the fourth solution, they are occurring in complex conjugates, we can always write the solution in the form of sine and cos, right. So, I get that this is also equal to C3, let me say that we will have a different constant altogether. So, C3 prime e to the power, well, not e anymore, cos of mt plus C4 prime sine of mt, right, where these two are different set of constants than these two. Okay. And then of course, where now we have got a family of extremals, I can find the CIs are found from the boundary condition, found from the boundary condition q bar of 0 is q0 bar and q bar of 1 is q1 bar, and each of them are set of 2 equations. So, we have a total of 4 equations for 4 unknowns, and that completes the discussion of this example. Okay. So, then another example Let us look at a special case, right. So, the special case is where L does not explicitly depend on T. So, of course, that is the case where we should have a Beltrami identity instead of the full Euler-Lagrange equation, and that identity must be the reduced order Euler-Lagrange equation. Okay. So, in this special case L, the integrand in the functional does not depend on T explicitly, right. So, I have that H is equal to summation from 1 to n, which is q k dot del L del q k dot minus L, right. So, this will be equal to a constant. Okay. So, this is, so we see that when L does not contain explicitly the T, the independent variable, then this, in this case the Beltrami identity is of this following form, where we have the summation over these variables q k's. So, this is my Beltrami identity,